Hello, welcome to this lecture. So we have two tracks running parallelly in this class. One is we're gradually understanding more quantum mechanics, and then on the other side, there are certain design principles for designing electrochemical materials, designing catalysis, and so on. These design principles use tools of quantum mechanics for material design. So this is again a first step where we integrate certain tools of quantum mechanics with a certain class of heterogeneous catalysts. So what I'm trying to do here is to give a lecture based on a review paper that I wrote some time ago. This review paper is meant to be an introduction to density functional theory, which is a version of quantum mechanics that is very useful for designing materials, and certain principles of catalyst design as applied to certain class of catalysts called the doped oxide catalysts. That's what I will try to do. So what am I trying to emphasize here? I'm trying to emphasize that theoretical principles, in this case density functional theory, can be utilized for designing class of catalysts, especially if we can compare certain aspects of this theory against experiments, with experiments. Okay, so that's the goal. So what is the outline of this lecture? So how can theory help heterogeneous catalyst design? And then I'm going to give density functional theory. Why I'm calling just as an advertisement is we, in the other track, right, as we unfold quantum mechanics, we will deal with density functional theory at a deeper level. Even with that, the whole this subject matter, density functional theory, you can have a one semester class just on density functional theory. So we would not be able to go to such a depth. However, we will typically the level at which we'll be dealing with is we should understand the underlying assumptions, underlying models behind density functional theory. And this is typically as it is implemented in the common software packages that will be used. Okay, so that's the level, and we will introduce some parts of it in this lecture, also in the review paper that I'll be distributing to you. I'll be sharing it with you. Okay, all right. And then I will talk about a case study which has been demonstrated some time ago. Design of a carbon monoxide oxidation catalyst. This is an important class of catalyst. Why is it important? Carbon monoxide is a huge poison. Okay, so there are many processes that give rise to carbon monoxide generation. They have to be completely oxidized to carbon dioxide. For example, in certain European countries or Western countries where they have severe winter and there are ways of heating based on wood blocks and so on. If these wood blocks are not completely combusted, they're only partially combusted, they give rise to carbon monoxide. And that can be a severe poison. Okay, so that's an important chemical process that had to be taken care of. So there's lots of effort that has gone into carbon monoxide oxidation catalysts. So we will talk about that. So we will also talk about some other work. Again, the whole point is not just for advertising. We are trying to illustrate how density functional theory can be used for catalyst design. And then I will give you a certain overview of what we have discussed. So in the review, I elaborate on two common ways of modeling surface chemical process. Okay? So for example, the surface chemical process as is relevant to heterogeneous catalysts. So this is one kind of models called cluster models. Okay? These developed from chemistry community, quantum chemistry community. So even though we are thinking about, let's say this is a molecule that is interacting with a surface. Okay, so a surface has it's a semi-infinite surface. It is infinite in this direction, right? In this direction. But even though that is so, that requires certain way of numerically representing the surface due to technical reason, as elaborated briefly in the review. That is not typically done in the quantum chemical software programs. Okay, so what is typically done is you represent a part of a surface only in this region. Okay, so even though there is the semi-infinite in this direction, you don't represent that. You represent only part of the surface, and then you represent that to the surface in a cluster. In this cluster, there is a limited region, okay, which is represented quantum mechanically, and regions far away from this cluster is represented using classical mechanics. Okay, so there can be, let's say, point charges and so on. Okay, what is called force field calculation. In this region, there is quantum mechanics. So what we are interested is in bond breaking, and this in the reactant and generation of products, and this bond breaking and transformation of the reactants to products occurs due to the interaction in this in the vicinity of this reactants in this vicinity. Okay, so this surface is the catalyst we are thinking about. So all the bond breaking is predominantly occurring due to chemical interaction of the reactant product along with the surface only in this region. So bond breaking has to be represented quantum chemically. So only this part you are representing, and there is no much of bonding changes does not occur in this region. So that need not be represented quantum mechanically. It can be represented classically. Okay, so this is one way of representing heterogeneous catalyst. Is one way of computing. Okay, the energetics and other properties of surface chemical process. As opposed to this, there is a certain other class of models called supercell or a slab approximation that came from solid state physics community. So in this case, the semi-infinite surface, this is a semi-infinite surface that is represented as a slab. Okay, so it is not only a slab, it's a what you call under periodic boundary condition. So what is periodic boundary condition? So there is a supercell which contains only this part. Okay, this part, the entire region is represented quantum mechanically, and it is of a certain size. Okay, so the periodic boundary condition is this is a periodic cell, and whatever happens here also happens in this cell and in this cell also. Okay, so because of periodic boundary condition, okay, this part is exactly the same as this part. This part is the same as this part. There's a certain periodicity in this representation. However, the entire part is computed using the methods of quantum mechanics. There's no classical representation here. Okay, so this is two different approaches towards modeling surfaces, and in time this has become more and more common, more and more accurate for representing surface chemical processes. So you should be aware. Okay, so in the early 1900s, 1990s, okay, there was sort of debate which is a better representation here. But in time nowadays, if you see, even the quantum chemical packages have adopted this kind of representation of the surface. So again, I've talked about density functional theory in my previous lecture. We will talk about it in much greater detail. So all the density functional theory relies on a particular theorem called Oerenberg-Kohn theorem. So where it was proved that energy of a many-body system is a unique functional of electronic density. Okay, so if you can get the electronic density correctly, and the energy can be obtained. The energy is just a unique function of electronic density. It was proved by some important theorem from quantum mechanics. So even though that was stated as a theorem, how do you get the electronic density? Electronic density itself is a function of the nuclear potential and so on. So the practical method was not illustrated. So from this theorem, to implement this theorem, okay, there is a practical approximation which is called the Kohn-Sham approximation. So it was so what they try to represent is the electronic density is represented using Kohn-Sham orbitals. Orbital is a one electron wave function. Using this one electron Kohn-Sham wave function, Kohn-Sham orbitals, there was a way to not only represent electronic density, certain other quantities like the kinetic energy of the electrons, okay, and other properties. You will just see in the next few slides. Was also, it was possible to estimate using this computational approximation. So that was a big breakthrough. Okay, so both these in both these breakthroughs, Walter Kohn was involved, and he got a Nobel Prize in much later. In later years, and this is the most powerful method of quantum mechanics that has been used in material design. It's extremely powerful. It started in physics and chemistry community. Now it's a very, very practical engineering tool. There are industries, there are companies which have been set up. All they do is use density functional theory to design materials of commercial consequence. Okay, so it's important. It's no longer a tool of sciences. It's a practical tool of engineering. Okay, like you use, let's say, computational fluid dynamics. Okay, which was developed in fluid dynamics community. Now it has wide relevance in engineering design community. Likewise, this has become increasingly prevalent in the engineering community. So to represent this Kohn-Sham orbitals, again internal electron density, there is certain class of functions, okay, called the basis set. Okay, because of this periodic translation symmetry, which was mentioned in the previous slide, you need to use a basis set of class of functions to represent Kohn-Sham orbitals and internal electronic density. This plane waves, okay, e to the power of ikx. Okay, that's a plane wave, right? So as you vary k, the periodicity of the plane wave changes. So that provides a convenient the symmetry of this plane wave, symmetry of elementary function, which is used for representing, let's say, Kohn-Sham orbitals and internal molecular electronic density. Okay, so the more an optimal function, the elementary function that is used for Kohn-Sham orbitals are the plane waves. This is, you must be aware of plane waves. Okay, when you do, let's say, Fourier series. Okay, so what, given an arbitrary function, what you do in Fourier series is you're trying to break down that function and represent it in terms of plane waves, right? So that is a very elegant set of elementary function that is used for representing Kohn-Sham orbitals. So, so another approximation is when you are thinking about chemical bonding. Let's say take an atom. Okay, let's say lithium. Okay, lithium has 1s2 electrons, 2 electrons in the 1s orbital, and 1 electron in the 2s orbital. So when you're thinking about chemistry of lithium, the 2s orbitals, okay, the electrons in 2s orbitals play a more important role compared to the electrons in the inner orbitals. Okay, so what you try to represent is the core orbitals are not represented, or in fact, the quantum mechanical representation of the core orbitals is frozen. Okay, only the valence electrons are represented accurately. Okay, so this is called pseudo potentials. Okay, so when you go to higher and higher, lithium has only 3 electrons. When you go to, but most of the important catalysts are, let's say, transition metals. Okay, they have lot of electrons, and most of the electrons are core electrons. Okay, it is not, the electrons that need to be represented more accurately are the valence electrons. Okay, so compared to core electrons, the valence electrons are represented more accurately, and all the effect of the core electrons are represented in terms of a pseudo potential. Okay, so how do you, that was an important breakthrough in this whole computational screen. How do you generate accurate pseudo potentials? Okay, so it is often called, along with density functional theory, you use PPP. Okay, so what are the three PP? One P is periodic. Okay, one P refers to periodic, and then the other P refers to plane waves, and the final P refers to pseudo potentials. Okay, DFT, PPP representation or way of computing things. Okay, so all the three things are important: periodic systems, plane waves, pseudo potential. So these are, I'm just talking about it qualitatively. We'll see slightly more quantitatively in this lecture, and then it will be elaborated much more quantitatively in few weeks. So as I said, density functional theory, because of its approximation, is very good for condensed matter. Okay, certain properties, solids can be done much better. Atoms can also be addressed here. It is good for computing energies, okay, but it's not that good for computing optical properties. Why do I say? So density functional theory is a theory for ground states, okay, and not for excited states. When we are talking about optical properties, usually there is an interaction between matter and radiation causes certain excitations, okay. The electrons are excited to higher level orbitals, and these excitations are not well captured by density functional theory. Much of the properties that are what are called ground state properties, okay, ground state energies can be well captured within density functional theory. So we are getting into more aspects of quantum mechanics. So as you are beginning to see in the other track in quantum mechanical lectures, all the properties that are of interest in quantum mechanics are represented using operators. All right. So when we are looking at simple systems like a particle in a box and so on, we are involved in, we are trying to use two elementary operators. One operator is for computing the kinetic energy, okay, of the wave function, and then another is the potential energy of the wave function. All right. So here, what are we interested? We are talking about an electronic structure problem. Okay. So the electrons arrange themselves in response to nuclear potential. Okay. So supposing if I have a solid and I'm thinking about the structure of the electrons, and the electrons arrange themselves because of its interaction with the nucleus and as well as how they interact between themselves. Okay. So if I look at to get the energy of this system, I need to first have the Hamiltonian operator. Okay. So we will see this. We get this just an introductory lecture. It's the first cut introduction to the mathematics of it. We will see this more elaborately in the next few weeks. Okay. So the Hamiltonian operator for this entire many body system has many components. Ion-ion interaction. First, I have ions that are fixed in space, and that's a certain class of approximation called the Born-Oppenheimer approximation. All these things are elaborated slightly more in the handout. Okay, the review paper I'll be distributing. So this is the energy of the ion between the ions. Okay, and then there is the kinetic energy operator of the electrons. T represents kinetic energy. The T of electrons is the kinetic energy of the electrons. Okay, and then there is the kinetic energy of the ions. Okay, and then there is the potential energy due to interaction between the electrons. There is a potential energy. V refers to potential energy. The potential energy operator due to interaction between the electrons, and this is due to Ex is the external potential. For the electrons, what is the external potential? The potential of the ions is the external potential. Okay. So these are the different components of the Hamiltonian operator. Mathematically, let us look at this. Okay. So this E ion, okay, corresponds to this particular term. Okay. So if there are two ions, okay, one has a ith ion and the jth ion. The ith ion has a positive charge equal to, let's say, Ci, and the jth ion has a positive charge equal to Zj, right? So this is a repulsive interaction between two positively charged ions. So, and which are separated by this internuclear distance. Okay, so this is from classical electrostatics, and then this term is the kinetic energy operator. Okay, so you should be able to recognize the kinetic energy operator here. Okay, and this term is the kinetic energy operator for the ions. Okay, so between the difference between this and this term is this corresponds to mass of the electron. This corresponds to the mass of the ions. Okay, so you should be able to recognize the kinetic energy operator. So let's look at the interaction, potential energy of interaction between two electrons. Okay, so so as opposed to this chart, there is a unit charge on the electron. So again, this is a repulsive interaction between two electrons that are at two different positions. These are the position vectors, Ri and Rj of the two electrons that are here, and this is an attractive interaction. Okay, because one electron is interacting with a nuclear charge. The electrons are negatively charged. It is interacting attractively with a ion which has Zi. The Ci is a charge on the ion, and so again it is the distance. This refers to the distance. This is the position vector for the electron. This is a position vector for the ion. Okay, so all right. So this is the mathematical expression for the Hamiltonian operator. So you would also gradually see. So this Hamiltonian operator operates on the wave function, many body wave function, and to get the energy, the expectation value for the energy, I use the Hamiltonian operator operates on this. We will see this more. Okay, so this is just the first 2 weeks of quantum mechanics. So we'll gradually understand this entire thing in much greater detail. Okay, so as we see, we are getting into battery design, we are getting into heterogeneous catalyst design. So for this, we need to know density functional theory. How does the density functional theory operate? Which again, we need to know something about quantum mechanics. Okay, so this is just like an introductory tutorial on this. Okay, so all this is supplemented with the review article that I have provided. This is a normalization constant. What is this symbol? This is called bra and a ket. Okay, so you will see. Okay, so this is normalized wave function. So we will again this explain slightly more elaborately in the handout I am providing. So density functional theory. So again, as I said, the total energy is can be represented as a unique functional of the electronic density. So and it has different components. Okay, the electronic density, as I said in the previous thing, it depends upon kinetic energy, Coulomb repulsion between electrons and electrons, ion-electron interaction. This is not a repulsive interaction. This is an attractive interaction. This is again the interaction is ions with other ion. This is again repulsive interaction, repulsive electrostatic interaction. And then this is a particular kind of interaction which is essentially quantum mechanics. All these things can be understood in some ways from classical mechanics, but this is inherently quantum mechanical. Okay, well, exchange interaction, you will see the electrons are fermions. Okay, because electrons being fermions, they have exchange interaction. Okay, you might have seen in high school called Pauli's exclusion principle. Okay, that is because of exchange energy, and then there is something called correlation energy. Both are these because are essentially due to quantum mechanical reasons. We will see in the next few weeks. We'll elaborate this much in greater detail. So again, I said this is just to give you an idea of the mathematical expressions that are involved. Okay, so I am not going to hold you responsible at this point of time for you to understand this, just to give you an idea again. So if you look at it, these things are not complicated. Okay, so this is the kinetic energy operator operating on a wave function. Okay, so you will see because the wave function can be a complex quantity. This is a complex conjugate of the wave function. Okay, and then this is just like electrostatic interaction. Okay, there is a charge density at some point, and it is interacting with another charge density at some other point. This is the distance between the 2 points, and then I'm integrating over all space. Ion electron interaction can also, this is the potential of the provided by the ion. It is interacting with the electronic charge density. Okay, so all these things can be understood from classical electrostatics. Ion interaction. Okay, so this can also be understood from classical electrostatics. Okay, so this is, I'm not going to hold you responsible at this point, but gradually as we progress in the class, we'll understand this better. Okay, so as I said, the last term, which is essentially quantum mechanical in origin, is exchange and correlation energy. So this, I'm talking about exchange. There are a lot of approximation. This is one of the frontiers of research in density functional theory. This is not typically research done by engineers. This is done by, let's say, chemists and solid state physicists. Okay, so at least you should be aware of this term called local density approximation. Again, we will elaborate this in greater detail in the next few weeks. Right. So, going from density functional theory to Corsham approximation. So we, what is the main approximation here? We are going to represent the entire electronic density using what is called Corsham orbitals. Okay, so that is the approximation. So this becomes like, so this is like a atomic orbital. Okay, instead of atomic orbitals, I am having Corsham orbitals. Each orbital, okay, can hold. When I say orbital, it's a wave function for one electron. Okay, it can hold one electron, and then so typically, if I talk about spin orbital, it can have upspin and downspin. Okay, so when I say, let's say, helium atom, okay, I have 1s orbital. It can hold, or let's say in this way, it can hold one electron of one particular spin. That orbital can hold two electrons of two different spin. Okay, it can hold one electron of a particular spin or two electrons of two different spin. Okay, so that is an when I go from in periodic table, when I go hydrogen, helium, lithium, beryllium, and so on, I have 1s orbital, 2s orbital, and so on. Likewise, here I am going to talk about Corsham orbitals. So why is this important? Once I define an orbital, all the terms, okay, relevant to the Hamiltonian can be computed using this orbital. Okay, so using this Corsham orbital, once I represent the electronic density in terms of orbitals, I can have a kinetic energy operator operating on the orbital that will give you the kinetic energy of that system. And then there is this orbital, the electrons are moving around under an effective potential. The effective potential is provided by what? Provided by the ions and the interaction between Hartree interaction, okay, between the electrons. And then there is a potential again, which is inherently, which comes because of quantum mechanics, exchange correlation, okay, exchange correlation potential. Okay, so there are three potentials here. These two are can be rationalized from classical electrostatics. Okay, there's an attractive interaction, there's a repulsive interaction, and this is inherently quantum mechanical in origin. Okay, so how do I define potential? Again, from classical electrostatics, when I have how energy changes when I bring in some charge. Okay, that's the way you define classical potential. Here also I am using some such definition. So this is just an introductory lecture on Corsham approximation. So we will look at this in greater detail. So the entire electronic density I am going to represent using Corsham orbitals. Okay, so the electronic density at a point is because of different electrons. Each of the electrons is residing in different Corsham orbit. So all these things are going to give rise to my total energy. Okay, so see, what did Hornberg-Kohn theorem prove? If I know this correctly, okay, I can get the total energy. The total energy is a unique function of charge density. Okay, that is proved by the Kohn-Oehenberg theorem. Okay, but that didn't tell you how to compute the density. Okay, that computing density was provided using Kohn-Sham approximation. What is the important approximation? That I'm able to represent the electronic density using Kohn-Sham orbit. That is the approximation. With that approximation, all the terms relevant to the Hamiltonian can be obtained. Okay, so that was what demonstrated in the Kohn-Sham theorem. Okay, so the okay, so again, slightly more additional slide on the pseudo potential approximation. Okay, so what did I say? There is there is a total wave function, let's say. So the total wave function is what is important. So where does the pseudo potential comes? Okay, so I'm going to represent only one part of the wave function. Okay, for every wave function, there's a core part, okay, which is the inner part, and there is an outer part, okay, like the valence part. When you are thinking about chemical bonding changes which are relevant to batteries and catalysis, there is an inner part of the wave function that is not changing. Okay, so there is a frozen part. There is a frozen core part, inner part. Using this frozen inner core, I am going to generate a pseudo potential, okay, which is going to break down the entire potential into two parts. There's the inner part which is not changing, and outer part which is being represented. Okay, so that is the idea behind the pseudo potential. Instead of the real potential, I am representing a pseudo potential. Pseudo means not the real potential, and this pseudo potential is accurate in what region? In the valence region, it behaves like the real potential, whereas at the inner region, it doesn't behave like a real potential. Okay, so there is an approximation which is used in the inner part, which is not important for chemical bonding, where in the outer part it is represented more accurate. Okay, so that is the idea behind the pseudo potential. Again, this is elaborated slightly more in the review paper which I'll be sharing with you, and we'll elaborate it more in the next few weeks. So the terms, okay, so this is typically when I implement this plane waves, okay, express everything in terms of plane waves. I take lots of Fourier transformation, and then the equations can get quite complicated. Okay, I'm just projecting this here. Okay, I'm not going to hold you responsible for understanding this this set of equation. This is just to give you an idea on what happens when you represent all these functions in terms of plane waves. Okay, e to the power of ix. Okay, so that's represents one plane wave. K is a wave vector. When I do Fourier transform on all these terms come about. At least, yeah, they can get a bit complicated at this level. You need not understand. Okay, just to give you an idea of the form of these equations. Okay, so eventually, what do you do? Okay, so you what is the approximate algorithm? You first, for this electronic structure density functional theory calculation under the plane wave periodic pseudo potential approximation, you first guess a trial wave function. Okay, so you guess the form of Kohn-Sham orbitals. You make a guess, and then using that trial wave function, you build up the charge densities. Once I build up charge densities, I each wave function, each orbital is obtained from an eigenvalue problem, right? So the eigenfunctions are all orthogonal to each other, right? So I use like Gram-Schmidt orthogonalization procedure to orthogonalize the wave function, and then once I have that trial wave function, I know everything to calculate the Kohn-Sham Hamiltonian. And then there are certain numerical procedures called preconditioning and so on. This you might have heard in your how you entire solve a matrix problem. Okay, you set up a matrix problem. There is a way to precondition the matrix to make it numerically stable, and then you use a minimization procedure. In this case, conjugate gradient method, and then use this minimization procedure to minimize energy. Okay, and then once you minimize the energies, you update the wave function, get the eigenvalues, and using this new wave function, quantum orbitals, you again build new charge density, and you ask whether it is the energies have been converged. If no, if it is not being converged, you again repeat this procedure. Okay, and then once you have this converged system, you use this converged electronic density to compute properties. Okay, so again, this whole thing, this whole algorithm, okay, can be, it will take a semester to understand in great detail. Okay, so that is not the time we have for that is not the purpose of this course. This course is meant to give you an appreciation what is the approximate algorithm that goes into the DFT PPP numerical methodology. Okay, so just to give you an idea, I projected this algorithm. We will go into this algorithm in greater detail, some parts of the algorithm in greater detail. Okay, so now this itself is a half an hour lecture. Okay, so I'll stop here, and then there is a second part to this lecture, which I will do in separate lecture. Okay, this review has two parts. Introducing you to some aspects of density fractional theory, and then the second part is how density fractional theory is used for designing catalysts in this using the doped oxide system. I will do it in the second part in another lecture. So I'll stop my recording here.